This presentation, conducted by Pole Zero Corporation, will demonstrate the communications range degradation in UAV-based radio relays when Cosite interference effects inherent to this type of radio relay application are overlooked. This drawing shows the equipment layout that will be used in this demonstration. On the right half of the drawing is the relay uplink with the corresponding downlink on the left half of the drawing. The only coupling between the two links is the retransmission cable coupling the audio signal from the uplink to the downlink to perform the relay function, and the RF coupling at the top of the chart, which simulates the 40 dB isolation assumed between the downlink transmit antenna and the uplink receive antenna. The following video will show the actual hardware used in this demonstration. Hello, my name is Tim Harrington. I'm a business development engineer for Pole Zero Corporation. Today I'd like to conduct a demonstration of a radio relay commonly implemented on unmanned aerial vehicles, UAVs, to connect distant warfighters. The backdrop in this video suggests a warfighter on a ship employing a UAV radio relay to contact a soldier on the opposite side of a mountain. The radio relay is comprised of two links, the uplink and downlink, operated at different frequencies. In this case, the uplink is from the ship to the UAV, and the downlink is from the UAV to the distant land-based soldier. In an ideal implementation, the range over which the relay operates would be determined by the ranges of the uplink and the downlink. Unfortunately, most UAV relay applications realize only a small portion of this range due to Cosite interference effects within the UAV. This interference is caused by the strong signal emanating from the UAV's downlink transmitter interfering with the UAV's highly sensitive uplink or victim receiver due to the lack of sufficient isolation between the relay's transmit and receive antennas on the UAV. The demonstration we will conduct now will show the communications range benefits of mitigating this Cosite interference on the UAV's victim receiver. We have laid out before you in roughly the same orientation as the backdrop, the uplink and downlink. Each link composed of two handheld radios, one in receive and one in transmit mode. The shipboard or ground user radios are shown closest to you, while the two radios used on the UAV are shown farther from you. The radios used in the relay have their audio signals coupled through this cable. Their antennas are coupled through two 20 dB attenuators in cascade to simulate the 40 dB between the UAV's radio relay antennas. It is this coupling of high-level transmit energy that degrades the sensitivity of the uplink receiver, creating Cosite interference. Each link is composed of significant attenuation to lower the transmitter's signal to levels appropriate for reception. The demonstration will measure the attenuation between the uplink transmitter and receiver required to get a minimally acceptable audio signal quality at the downlink receiver, with or without Cosite interference mitigation. The RF switching on both links, shown here, will either apply or bypass Cosite interference mitigation hardware to these links, and we will observe these effects. Since the most vulnerable receiver in the relay is the uplink receiver, the downlink attenuation will be selected to ensure that the downlink receiver is operated 10 to 20 dB above the receiver's sensitivity to isolate the Cosite interference effects on the radio relay. An audio signal will be introduced by the communications system analyzer at the uplink transmitter and analyzed at the downlink receiver for its signal to noise and distortion or SINAD value. A value of 12 dB will be considered the minimum acceptable signal quality level as given on the communications system analyzer. We will conduct the demonstration while operating the 30 to 88 MHz frequency band. The downlink will be operated at a fixed mid-band value of 50 MHz, and the uplink will be operated at various frequencies from 30 to 88 megahertz. For this demonstration, the uplink will be operated at 32 megahertz. To measure the UAV's uplink victim receiver sensitivity, we will transmit from the uplink transmitter at a fixed output level, followed by a variable attenuator. The amount of attenuation applied with and without Cosite interference mitigation required to yield 12 dB cyanide at the downlink receiver will determine the UAV's uplink or victim receiver's sensitivity with and without Cosite interference mitigation. Presumably, if Cosite interference is degrading the UAV's victim receiver sensitivity and therefore the radio relay's range, it should take less power from the uplink transmitter with Cosite interference mitigation than without to achieve the 12 dB output cyanide we desire. We will now make this measurement. All right, let's begin to do our demonstration here. Recall that the uplink is basically on this half of the table and the downlink is on the other half of the table. This is the uplink transmitter. Its output goes through a network of fixed and variable attenuators, couples into this switching matrix here, which either can bypass or apply the Cosite mitigation unit, but ultimately the signal goes to the uplink receiver. Now the uplink receiver's audio output is coupled into the downlink transmitter, which will then feeds the downlink system. But recall also that the antennas are coupled with 40 dB isolation between their representative of the coupling between the receive and transmit antennas on the UAV. So we have this cross-link coupling, if you will, that applies. So once the audio is coupled into the downlink transmitter, it goes again to this switching matrix, which will either bypass again or apply the Cosite mitigation unit on the transmit. The output signal comes through this power meter. We should see nominally 5 watts of output power. That signal couples through this attenuator network and goes to the downlink receiver. The output of the downlink receiver, which is audio, is fed into the communications analyzer to determine the quality of that audio. And again, we're looking to get an audio quality, a cyanide, in excess of 12 dB. All right, so let's look at the case where we're bypassing both Cosite mitigation units, but we have the 40 dB coupling between the two antennas. We're going to key the system, and we'll note at the power meter that we have approximately 5 watts of output power, which is what we would expect. That's downlink output power. The audio is coming into the communications analyzer, and if we look at the cyanide reading on the communications analyzer, we have no attenuation on the uplink transmitter. We see that we have a cyanide value in the high 20s. So we'll add some attenuation to the uplink transmitter. I'm going to put in 20 dB of attenuation. And when I do that, we're at about the 12 dB level. I'm going to call that 12 dB. So for the case of no Cosite mitigation, we're able to attenuate the output of the uplink transmitter by 20 dB and still get acceptable audio quality from the system. All right, now we'll look at the case where the Cosite mitigation units are in the circuitry. If you recall, previously we had 20 dB of attenuation on the uplink transmitter, which yielded 12 dB of cyanide. We've left the 20 dB in place, but now again we have the Cosite mitigation units operating. So as I key it, we find that we do have our 5 watts of output power for the downlink transmitter, but the 12 dB we had for cyanide now is much better. It's again like the high 20s, reflective of the fact that we're mitigating some of the Cosite interference. But to quantize how much we've mitigated, let's add some additional attenuation. I'll add 10 dB more, and we see we're still in the 20s, and I'll add 5 dB more. We're in the 18, so we've added a total of 15. Let's add 3 more, which would be a total of 18. So that's 18 dB we've added beyond the 20 we had previously. It's still a little high. Let's add 1 dB, which would be a total of 19. And I'm going to call that 12 dB. So we've added an additional 19 dB of attenuation on the uplink transmitter and still achieve our 12 dB of output cyanide. If we translate the uplink attenuation levels used in the two cases presented in the demonstration to actual signal levels at the uplink receiver by subtracting the attenuation levels measured in the demonstration from the uplink transmitter's output power in dB, we can determine the signal level at the uplink receiver required to support 12 dB SINAD at the downlink receiver. This chart shows these levels on the vertical axis for the two cases shown in the demonstration, with or without Cosite interference mitigation. Additional data is shown for several uplink frequencies beyond the 32 MHz case shown in the video, all with a fixed downlink frequency of 50 MHz. Given that the nominal sensitivity of the radio used in this demonstration is -116 dBm, we can see that, despite the presence of Cosite interference, the Cosite mitigation units restore the UAV's uplink receiver sensitivity to its specified performance level. This chart shows data derived from the same setup as the previous chart, but for various frequencies in the UHF band with a fixed mid-band downlink of 300 MHz. While we can see that significant uplink receive desensitization occurs due to Cosite interference, as in the previous VHF results, the UHF results raise an additional issue for relays with insufficient isolation between the uplink and downlink antennas. This issue is regeneration, which is observed at virtually every uplink frequency without Cosite interference mitigation. Regeneration occurs when the downlink transmitter's carrier and noise energy, once keyed by the uplink receiver sensing a receive signal, is sufficient to continuously key the downlink transmitter through leakage to the uplink receiver. When this occurs, the radio relay is locked up, and the radio relay power must be recycled to regain control of the relay. Obviously, this can be a significant problem with an airborne relay, as the relay is essentially non-functional when regeneration occurs. Setting aside the potential issue of relay regeneration, what is the effect of uplink receiver desensitization due to Cosite interference to the communications range of the radio relay? Assuming an inverse square law relationship between received power and distance, this chart shows the remaining range for a communications relay designed around the uplink receiver's specified sensitivity following the receiver's sensitivity degradation due to Cosite interference effects. For the demonstration case just presented, a penalty of 19 dB occurred due to Cosite interference effects. This chart shows that a penalty of 19 dB yields approximately 10% of the range expected by the link's designer, who assumed full receive sensitivity. Expressed another way, a tenfold increase in communications range could be achieved for this radio relay by mitigating the Cosite interference effects presented in our demonstration. Obviously, if the UAV relay antennas are more closely coupled than the 40 dB assumed in this demonstration, even greater range penalties would occur. We hope this presentation has been useful to you. If you would like to discuss specifics of your application, please feel free to contact me at area code 513-870-4076, 513-870-4076, or via email at support@polezero.com. Thanks for your attention.